Okay, okay. Hello, everybody. This is Professor Ma, and this is the sections on alternating series and conditional convergence and absolute convergence. Okay, so uh, alternating series is a series where the signs flip-flop between positive and negative terms. So here's example. Okay, so it looks like that. Okay, where the a's are positive numbers, so you have minus, plus, minus, plus, plus, minus, plus, minus. Okay, where do they show up? I mean, why plus, minus, plus, minus? Why not plus, plus, minus, plus, plus, I mean, 2 plus 1 minus 2 plus 1 minus, or some other patterns? Well, they show up, comes out of, you will see, come out with taking derivatives. And as see another one of those things which you do an even number of times, you get a sign, you get odd number of times, you get a different sign, flip-flopping of signs. Okay, so they show up naturally. That's what I'm trying to say over here. Okay, so we want to talk about the convergence of alternating series. Okay, and turns out there are two types of convergence. Okay, and first, the main theory is about the convergence of alternating series is that if I have a decreasing sequence, okay, the absolute value is positive number is decreasing, going to zero, and then if I were to put plus and minus sign alternating between them and add them up, the sum converges. Okay, and the the condition that it has been decreasing, that this AN has been smaller and smaller, is because it prevents them to keep doing something, jumping out, oscillating, to keep jumping out to above certain numbers out of a particular um, mm, yeah, just prevent it from jumping up and down. Okay, so here's a typical, the most probably important example to keep in mind is the alternating harmonic series. Okay, and this particular series, according to the statements, because 1 over n goes to 0, and then the terms is 1 over n, it goes to 0, and so I put plus and minus in front of them, and then from the theorems before, the limit exists. Okay, and we're going to demonstrate that actually on a visually. Okay, so actually it's more interesting. So we start with 1. So come from 0, go to 1. Okay, so that's the first term. That we're going to add 1 minus a half. So we step backward, half a step. But I'm going to plus a third. So we're going to add a third. Add a third, we're going to step back plus a third. And notice, because the terms are decreasing, so every time I jump back and forth, it's within the boundary of last time. Okay, so again, I mean, if I, when I add 1/3 to it, it's going to only up to here. It's not going to jump out of there. That's the reason we want the sequence to be decreasing in the process. So as we do this, we keep getting points that's within the previous boundaries as they go down, zoom down to a smaller and smaller funnel to a limit. So the limit exists. Okay, so this is a visual proof, if you like, of the statement we just had, that alternating sequence with the absolute value equal to 0, and then the alternating series, plus minus, the limit exists. Okay, so by these funneling actions, so the sum must zoom in at a point. Okay, but there's interesting things about the alternating series is that there are different type of convergence. Okay, the ones we just had, the alternating harmonic series, if I were to put absolute value around it, okay, if I say instead of having minus this over there, I just slap absolute value, that means I'm looking at sum of 1 over n. But that's the harmonic series, and that diverges. Okay. But on the other hand, the second series is the geometric series, okay, of with I equal to 1/2. So this is I equal to 1/2, 1/2 to the n series, and this converges. Okay. So there's something there for these characteristics, that is the alternating series converge, but the absolute value diverge. If that happens, we say these particular alternating convergence, we call these conditional. Okay, so here we go. Given an alternating series, for instance, like this one, I don't know how to give my brush highlight. And if I were to put absolute value around it, no problem. Plus 1/4 plus, it still converge. Okay, if that's the case, then we say this series converge absolutely. Means it converge with absolute value. Absolutely means converge with absolute value around it. Okay. Treating all the negative ones as positive. So it's really, really converges. Okay. But in the case of the harmonic series alternating, we cannot turn the negative signs around to positive, because if that's the case, then the series will diverge. So that's, by that, we say the series converge conditionally. That is, the alternating series is self-converge, but the absolute value, but the absolute value diverge. Okay, so basically, this is the things you have to sort out if you are given a problem to discuss whether the alternating series converge or diverge, conditionally or absolutely. Okay. So, so in particular for the harmonic series and the P series, okay, so it converges conditionally when P is equal to 1. So basically, when we turn plus or minus, then the series actually converge at the case equal to 1. Okay. This puts alternating sum of 1 minus 1 minus 1 plus 1 minus 1 plus 1. Okay, we say this diverges. Okay, why? Because the terms doesn't go to 0. The an absolute value an goes to 1. So even though I know what the answer of these series is at any finite point, okay, 2 of them is 0, 3 of them is minus 1, 4 of them is 0, 5 of them is minus 1. I know what the sum is, but we still call this entire infinite sum divergent sum. Doesn't add up to anything specific numbers. Okay. This particular sequence, okay, alternating sequence. So because the limits these go to 0, and you can show it's decreasing. So therefore, sum of these an converges because it's a decreasing sequence, and the an go to 0. Okay. So you have to justify over here. I guess in this case I didn't do it, but you have to show this decreasing also. Okay, so decreasing. This sequence is decreasing. But that's pretty easy. You can use ratio test or take the difference. Now, next we want to identify what type of convergence is the sum. Okay, and so we're going to use, so in other words, we're going to use first to look at because the alternating series. So we're going to look at two things. We're going to look at the absolute value of A. That is, we just drop these in the sum of 3n over n squared plus n minus 1. Okay. We want to know if these converges or diverge. If these converges, then the original series converge absolutely. If this diverges, then this diverges, then this original converges conditional. Okay. So let's look at the absolute value of the sum. And to determine the absolute value, sum of the absolute value, we throw away the non-important terms and basically throw these away and use limit comparison theorems. We're going to compare these to that. And then, of course, in these limits, sorry, my pen is acting up kind of funny. And you can see the limits 1. Hence, these two series are comparable. So summing, but summing multiple each other. But the sum of this series, this is basically harmonic series. So it diverges. In other words, the original series with alternating sign converges conditionally because of these diverges, and that imply, of course, the sum of these positive term diverges. Okay, and so the sum of the positive term diverge and the sum of the alternating converge. So these two together says, these conditional convergence. Okay, so okay. So this is a summary what you do with the alternating series and the steps. And so if you understand what happened with the positive series, and then this is kind of obvious. You just have to do 2 checks. Okay, that's it. Okay, bye-bye. And